in Chapter 7 of Volume 1, Rational Expressions. The first thing we do is we look at what's called fractional expressions, and when we have one over another of algebraic expression where the denominator is non-zero, then that is what they call fractional expression. If the numerator and denominator are polynomials, then we are dealing with rational expressions. This chapter will deal with rational expressions. Rational expressions are very, very helpful when we study calculus. In fact, we do a little bit of work with calculus in this chapter. What happens is when you're looking at calculus, there's a lot of tough concepts, and our CAS calculator will make these tough concepts easier to learn by letting us view these things graphically and letting us view these things with the various calculations. Okay, let's take a look at the Scratchpad screen that we have right here. We're going to go over a little bit about graphing this stuff, but for right now we're going to take a look at the Scratchpad screen. We have x cubed plus 2x squared minus 8x over 2x squared minus 8. If we take a look at this expression, and if we factor out of the numerator an x and factor out of the denominator a 2, we end up with this expression. Then by using our rules from the last chapter about factoring, the inside term, 1 times 8 is 8. Things that make up 8 are 1 and 8, 2 and 4. Because of the way things are set up, we need to subtract these. So the one that we want is 2. Since the front is a 1, these will be our answer. Then when we have something over itself, we can drop it out, except for we need to pay attention to that it's not equal to 2. Because when we drop this out, if we put 2 into the original expression, we'd have division by 0. But if we put 2 into this expression, we do not have division by 0. But once we add that it's not equal to 2, that is what's happened. So when we're over here looking at this particular graph, there's going to be a hole in the graph at 2 and 1.5. But because of the details of the graph right here, it does not show the hole. But we'll go over a little bit later how we can find this particular hole. When we're dealing with calculus, we're going to be dealing with the concept of limits. We're going to be dealing with the concept of continuity. We're going to be dealing with the definition of a tangent line and the definition of a derivative. Now again, this is an algebra course, so you're not going to have to know all those details. But this is what happens in a calculus class. The places that we learn material in college algebra are all used in a problem. So if we have any holes in our knowledge, they come back and cause us problems in a calculus class. Now that's one thing very nice about our CAS calculator, because it will be able to handle this. So when we're looking at the concept of continuity, we talked about that there is a hole in the graph here at 2, but it's not shown. The other concept for calculus class is right here. When we look at how this factors, and we have the x minus 2 and the x plus 2, at x equal negative 2, there is a break in the graph. So again, when you're studying calculus, you will look at breaks, you will look at holes in the graph. And another thing that they can actually do in calculus class is they can use a piecewise definition, make this function even more complex, and put a point in here. So then the graph will jump. So you can have where we have a break, where we have a hole, where we have a jump. And then we can define graphs with piecewise definitions where they end up having sharp corners, where it'll go up to this point and then the graph will turn, okay, in here. So we can have places where they have sharp corners, and if these two don't meet and we use a piecewise graph, then we can end up with, okay, a gap in the graph. So the graph could go up here and we could have gaps. So in the places where there's gaps, in the places where there's holes, in the places where there's jumps, and the places where there's break, the graph is not continuous. In places where the graph is not continuous, we're not going to be allowed to use our derivative. We can only use it on the intervals where it's continuous. So all this stuff's going to come into play in a calculus class. Again, at this point, all we really need to know is that this expression and this expression are equivalent, since we said that x is not equal to 2. So there's a hole in the graph. Now, if you multiply this out, x squared plus 4x over 2x plus 4, and you go over to our calculator and put this into our calculator, you can see that it's the same graph. Underneath the menu on our calculator, there is a trace function. Again, I won't do the trace function at this point in time. We'll just look at the results of the trace function. So we can see that it traced out 0, 0. We set the step to be equal to 2, and it traced out 2, 1, 5. So this one does not have the restriction on it. Let's turn to the next page and look at some more information. On the next page, we go to our Scratchpad screen and we type in f1 of x. So the f1 of x was defined in the graph program. We talked about before that we could define functions with the store. We talked about before that we could define functions with the define in the menu, and we talked about we could define functions with colon equal. But before, we did not mention that we could also define functions inside of the graph application in the Scratchpad, or the graph application for the documents pages. So when we type the f1 of x, even though we typed the thing in with x cubed, it came back here and it came back with a warning saying that the domain of this answer may be larger than the domain of this answer. So what happens is, if we want to get rid of the warning, we type in that x is not equal to 2. And if we type in x is not equal to 2, then we no longer get the warning. If we type in f1 of 2, it goes back to our original function, and our original function, you cannot substitute in the 2 because it caused division by 0, so that way it comes out with undefined. But if we go to this simplified answer and substitute in with x equal to, it tells us that 3/2 is the answer. So the hole in the graph is actually equal to 3/2. The f1 that we're talking about is our cubic function, not the f1 over here, which is the reduced form. Let's go ahead and turn to the next page and look at it. We see on the next page our cubic function in our Scratchpad, and we see us attempting to trace out this particular point. We cannot trace out the point on the graph because it's undefined. So we just show a point that's close to it. If we actually put in the trace function and put in an interval to be 2, it will come out with 2 and actually say undefined and draw a vertical line. You might want to try that for yourself. Okay, the next thing we're going to do is to simplify radical expressions. So if we can factor them and have the same factor in both the numerator and denominator, then we can eliminate that particular factor. Here's an example of us doing that. So we have the difference of 2 squares, so that's 3x minus 1, 3x plus 1. The top, we will use our factor by regrouping technique. Again, I'll let you take a look at this, okay, and see that this turns out for the 3x squared minus 7x plus 2 to be equal to x minus 2 times 3x minus 1. and then it's put over the bottom, and the bottom both have 3x minus 1, so this reduces to x minus 2 times 3x plus 1. We said earlier we're not always now going to put the restriction on when we write the answer out, but when we start using our calculator, we're going to have to handle the restriction, because our calculator will give us a warning. So if we do not want to have the warning, we will have to take the restriction and say that it cannot be equal to that. So the 3x minus 1 dropped out. We set it equal to 0, so 3x equals 1. So x equals 1/3 would cause division by 0 in the original problem, but not in this reduced problem. So we have to say it like this for it to not say the warning. Let's go ahead and look at this on our calculator. So we'll go to the home screen. Then we'll go to the current document. And we see that when we type this in, we get the warning, and we get the answer x minus 2 over 3x plus 1. When we write that x cannot equal to 1/3, we end up with the answer over here. Turning to the next page, we go over multiplying rational expression and dividing rational expressions. So we end up just multiplying the two terms in the top, two factors, and the two factors in the bottom. When we divide it, we invert and multiply, and then we end up multiplying like we did here before. So to multiply these two, we factor them, then we look for things that cancel out and reduce our answer. To divide these, we factor them, we turn this upside down, we look for things that cancel out, and then we write our answer. To put these into our calculator, we enter these in and work them out. Let's go ahead and take a look at it on our calculator. So we can see the last one turns out to be x minus 4 over x plus 3. So we put it in, and then when we hit the enter, it flipped the answer into a compound fraction. And if we scroll up, we can see that the top answer is the same here. Let's flip to the next page on adding and subtracting. If the problem already has the common denominator, we're just going to add these two together. If the common denominator is not the same on the bottom, we're not going to get the lowest common multiple. We're just going to multiply the two on the bottom, then do the cross product, a times d plus b times c. If we're subtracting, this will be like a negative number, so it will be handled the same way. We do want to always get the least common denominator, the lowest common denominator when we're working these problems, otherwise it'll be complex. But if this is the lowest common denominator, then this technique is handy. We're first going to look at a problem in arithmetic. So in arithmetic, we're going to factor the 20, we're going to factor the 15, then we're going to multiply the first one to get the lowest common denominator. We're going to multiply the second one to get our lowest common denominator. Once we have our lowest common denominator, then we're going to add the numerator and end up with the answer. Over here, we're just going to multiply the two, then go down, 3 times 9, go up, 24, and end up with our answer. Let's go ahead and take a look at this on our Scratchpad. So we'll go over to our calculator, then we'll go to our Scratchpad. We'll press it again to switch it to the calculator part from the graph part. To put this in, we'll use Control and our fraction template, 3/20ths, move down 20, move over add, fraction template, 2/15, enter, get 17/60, fraction template, 3/8, move over, add, 4/9, move down, press enter, get our answer. We can also use it to help with our work. Go to menu, go to number, go to least common multiple, number 4, type in 20, type in a comma, 15, press enter, shows that our common denominator is 60. We can also use it to help with the factoring of these numbers. So go to our menu, go to number, go to factor, number 3, type in 20, press enter, and get 2 squared times 5. Turning to the next page, we will use the same technique on rational expressions. So we will factor, we will look at the common denominator. We will need in the first part an x minus 2 times both the numerator and denominator. For the second part, to get our common denominator, we're going to need an x plus 2. Okay, then taking 1 times x minus 2 and 1 times x plus 2, adding these two together, we end up with this answer. In this case, where they have no common factors, multiply the 2, go down, start up here, and take x times, the x plus 1, minus 2 times the x minus 3, x times x is x squared, x times 1 is x. Use our mnemonic for negative numbers. Minus 2 times x is minus 2x. Minus 2 times negative 3 is positive 6. Use our mnemonic for money. 1 take away 2 is minus. So the answer turns out to be this. Let's take a look at it on our calculator. Go to our home screen. Go to our current. This is example 3. So move ahead 1. And we see that these answers here, what they turn out to be. Let's take a look at it in a minute. We see that the second answer turns out to be it's the same as our B answer. We must use the common denominator command, and when we use the common denominator command, it doesn't factor the denominator, so to get our answer to look like what we wrote over here, we had to use factor. Let's scroll up. And again, we see we used the common denominator command. Then we had to use the factor command to get our answer to look like it did over here. Let's turn the page. And then we can look at our calculator screens shown over here, showing the same thing that we talked about, using common denominator and using factor for both parts to get our answer to look identical. The next thing we're going to look at is compound fractions or complex fractions. So compound fractions are where the numerator and denominator of both are composed of algebraic factors. So there's several different ways that we can use when we have these situations to simplify these. So again, take a look at these different methods that are explained in the book. We're now going to go over some uses of this from calculus, because the main place that this stuff gets used is in a calculus course. Now again, in your algebra course, you're not going to have to do the calculus part of these problems, but to be complete, we put this in here. The definition of slope, which will be covered in future volumes, is y sub 2 minus 1 divided by x sub 2 minus x sub 1. Now if we call the one point A and f of A, and then call the point that's h distance away from A plus h, and substitute this into our function f of A plus h, and if we take y sub 2, which is this one, minus y sub 1 over x sub 2 minus x, we end up with this formula for what they call the secant line. The secant line is a graph that will cut the function in two different places. When you study calculus, one of the concepts that you study at the very beginning is the concept of limits. So if we take the limit of this as h approaches 0, provided the limit exists, we come up with the slope of the tangent line. To find the slope of a tangent line, we need to evaluate the limit as h approaches 0 for the secant line. So if we had a function like f of x equals 1 over x minus 2, we need to find the slope of the secant line first for the point that p1 a f of a, p2 a plus h. So let's take a look at this on the next page. This is where we get problems in an algebra class where they just show us the problem written like this, but it actually comes from this definition of a secant line, and then the final thing is we come up with a tangent line. So if we're dividing by h, we can switch this into invert and multiply times 1 over h in here. Then this numerator part, we'll just take the first times the second, and then we'll take the 1 times a minus 2 minus 1 times a plus h minus 2. Combining like terms in here, we'll end up with minus 1 over a plus h minus 2. So this is where we would stop in a college algebra class. We would start here. In this case, when we're dividing by h, the method that one would be to invert and multiply. The calculus actually isn't that hard. So as h approaches 0, if you can, you just substitute in the h to be 0. So when you substitute in, you end up with a minus 2 twice. So this answer for the tangent line turns out to be minus 1 over a minus 2 twice. We're going to add this function 1 over x minus 2 into our Scratchpad graphing app to take a look at it. And we're also going to add a vocast library that has to do with finding equations of secant lines and tangent lines and so forth. Our calculator has a built-in equation of a tangent line operation, but putting our own in will help us understand what's going on. And they don't have a secant line and so forth, so there's some value for us adding our own library. So let's turn the page here. And so we bring back this function on our calculation Scratchpad by typing in F1, and it says it's in here. We added some functions to our library. So our library will let us find the slope of a tangent line, the slope of a secant line, minimum and maximums, things called inflection points, increase and decrease, and second derivative, and all kinds of things that we added to our library. Let's turn to the next page. So when we come up with the slope of the tangent line, it's built into our volume library, and it only works on CAS, so that's why we have this suffix on it. And then we call this up. So when we put that entry on the last page and pressed enter, it found our library that we were looking in, and it found the function that we put into our library. And if we wanted to find the slope of the secant line, it comes up with this answer here. Then if we use the common denominator on this particular slope, it comes up with this, and then if we factor it. So this is a way that we could actually come up with the same manipulations that we showed you several pages back. So when you get to a calculus class, you will be doing these manipulations in the middle of your calculus problem. Let's flip to the next page. The next page has us adding this library. Here we have a picture of the library actually being used. So what's going to happen is we're going to have the graph of a tangent line, okay, here, which is going to be 4 minus x. We're going to have a graph of a secant line at the point x equal 1, 2, 3, which cuts it in 2 different places. And again, here it shows us defining our library. Flipping to the next page, we see that when you type these in, this is the computer version of the software as a document form rather than a calculator form. It will also say done. But again, to make this print be a little bit bigger, we cut off the done. So we define the secant line, okay, slope as f of a plus h minus f of a over h on a calculator page. We define the tangent line as the same one here as the limit as x approached this. Then we did a formula for lines is y minus y sub 1 equals m times x minus x sub 1. And if we solve this for y and put in x sub 1, y sub 1, and m, we can come up with the point slope formula for a line. And then by plugging in, okay, the x sub 1 and y sub 1 to be x sub 1, f of x sub 1, and then for the slope, we plugged in the slope of the secant line. We could come up with the equation of the secant line. Doing the same thing for the tangent line, if we plugged in the slope of the tangent line, we could come up with the equation of the tangent line. So this is where we're taking global functions and putting them together to come up with a library of functions that we can use. And this tells us in here how to do that. So again, you're going to need to read in the guide how this is all set up. For your college algebra class, you're not going to need to have this. But again, when you get to calculus class, these building libraries like this will be very, very useful for you. And technically, we can use these libraries in our college algebra class. We'd be using what they call a black box. So we'd be calling this stuff up, getting answers. Now the problem with doing black box stuff, if you don't understand all the underlying concepts, you can misuse the stuff and end up using it in places where it's not allowed. Like in a calculus class, okay, you're going to have for the derivative and some of this stuff to exist, you're going to have places where it's continuous over an interval, but again, it cannot have like sharp points, it cannot have vertical tangents, and so when you study calculus, there's all kinds of details. It's going to be necessary but not sufficient for it to be continuous over an interval for you to use calculus on, and you're going to learn that the tangent line and the first derivative are going to turn out to be the same. Okay. Once you start setting up libraries, if you want to keep them isolated a little bit from each other, what happens is when you have global functions, you can build up like sets of libraries where the one will use a function that's in a different library in the middle. And then if you ever have to go back and modify, you only modify this one function. If you did it the way that we were doing it on the previous page, then you'd have to go to each library and modify something if you made a mistake or you were changing it. So the better way to build these out is to separate these. Again, this is going to be something when you get more advanced that you're going to want to use these kind of options. So you can kind of look it over here and see it. This is the way that programmers would prefer to write code. So initially, this might be a little too much. You might be better off just looking at the previous page instead of breaking this down like we did here, like programmers would like to write it. So when we call up our function for secant line with 3 and 2, it gives us the equation of the secant line. Then if we use define, go up here and just type this part in, then we get F2 to be the secant line. If we bring up from our catalog the tangent line and then type this part in, and then we can go over to our graphs and graph these and come up with the answer. So this is pretty neat that we can add all these little functions that are going to help us do a lot of things in a calculus class. This is the definition of a derivative. So again, we talk a little bit about calculus here, and we talk about the different symbols that people use for calculus. And so when we're having to, find a derivative for this function, we're going to use this f of x plus h minus f of x over h, and then we're going to take the limit of this as h approaches 0. Well, in your college algebra class, this is the only part that you are going to see. So again, it's just like the tangent line. So when we're dividing by h, we multiply by 1 over h. We take this part, the first two times each other, then go down x squared, subtract going up this part, multiply x plus h out, then take it times a negative 1, then combine like terms, and then factor out. And then to take the limit of this particular problem, you'll plug in at h to be 0, so you get a 0 here and a 0 here, so this answer turns out to be minus 2 over x cubed. When you're in a calculus class, you will learn simpler ways by rules rather than have to do this out by the definition. Also, your calculator can use the derivative function of the calculator to come up directly with this answer. Let's take a look at this on our calculator. So we'll go Control and flip to the next page. And here we see our answer for the tangent being minus 2 over x cubed. We see that the tangent gives us the same answer as the derivative, so we didn't type in the derivative formula, we just used the tangent formula. And we had a little bit of problems when we were manipulating this, so we did it for a, and then we substituted an x in for a to come up with this answer. If we go up a little bit more, we'll see that we defined a function to be 1 over x squared, and that's how we worked the problem out by using our calculator and the library that we put together. Okay, turning to the next page, we see that here's a screenshot of what's shown over here on our calculator. The next problem we have in here is simplifying this rule. Once you are in calculus, when you use the limit definition, you can see we had compound fraction. Once you learn to use the long definition, then later on you will work things out by memorizing like rules, like power rules and stuff for working problems out. And one of the rules that you use is the quotient rule. The bottom squared, the bottom times the derivative of the top minus the top times the derivative of the bottom. So when you're in your college algebra class, you will see where they give you a problem like this. Well, this problem actually comes from using the quotient rule, okay, here. Now, we're going to use method 2 to simplify this compound fraction. So we're going to switch this negative 1/2, since there's a term, into this term having a fraction. Then we look at the common denominator for the whole problem. So since this is the only fractional part in this whole compound fraction, we're going to multiply the numerator and denominator by x squared minus 1 to the 1/2 to clear this out. So we're going to have to take this times the first term, and we're going to have to take this times the second term. Well, the second term, of course, is the easiest one because this cancels out and you just end up with x to the 4th. And times the first term, this is 1/2 and this is 1/2, so we're going to add the exponents and get 1. Then we got 3x squared times this, and on the bottom, this will be a 1, which will be 2 over 2. So 2 over 2 plus 1 over 2 is going to turn out to be 3/2, and we end up with this answer. Again, we mentioned that this would be the bottom squared, the bottom times the derivative of the top minus the top times the derivative of the bottom. Well, here's the original function from a calculus class. So let's go over and turn the page. And we defined it in our graph function. So we'll go over to our calculator again. And we see that we typed it into our calculator and did some work with this function. And this function is quite complex to graph. The x cubed over x squared minus 1, okay, is graphed in there. Let's go to the next page. And the next page, we're going to see some work with this function. So if we take a look at this particular function here with the first derivative, we see that we end up with this answer right here. And our calculator over here is showing us the calculator way of doing it with the derivative, and then it's showing it where we put it in with the first derivative. We actually put it in with the first derivative to make it easier to follow the other global functions that we were adding to the library. Flipping back to the calculator screen, we'll just use this one that's shown here rather than flip it back over here on our emulator. So we have our original function that's in here, x cubed over x squared minus 1. Then we have, like, for this area, a relative maximum, a relative minimum for this part of the curve. We have where the graph is increasing. We have where the graph is decreasing. We have where the graph is increasing, and we have where the graph is decreasing. Now, you have to be careful, because when we start doing some of this manipulation, our calculator will substitute in where there's some warnings, and some of these answers will not be correct. So you have to be somewhat careful, because since the original function was undefined between 1 and minus 1, we cannot have the graph increasing and decreasing at those particular spots. So again, you have to watch out, because there's warnings over here on our calculator when a lot of this stuff is going on. So again, you have to do this stuff manually as well as do it with your calculator to help you. And then you have to take a look at stuff and draw some conclusions yourself. Again, this is the kind of stuff that happens to you in a calculus class. Luckily, right now you're only in college algebra, so you're not going to have to worry about that particular part. Then concave up, concave down, okay, whether it holds water or whether it doesn't hold water. So this one here is showing concave down, and this one is showing concave up. We set it equal to a sine function, and that allowed us to draw this kind of information on our picture. So again, these routines are helpful, but you must analyze the information, because of the warnings. It will show you information that's not correct. So again, you have to know what's going on. You cannot just take the black box approach and say that this is the correct answer. Again, here's the library where we added the first derivative and the second derivative. So we added this to make it easier to read our first and second derivative in these formulas. To find the X intercept, we set the function equal to 0 and solve for X. To find the minimum and maximum candidates, these are not going to be, okay, all the places. There's a type 1 and type 2, and these are candidates. A candidate does not mean that it's actually going to turn out to be a minimum or maximum. So again, these functions are helpful, but you have to use these with your knowledge of what's going on. Otherwise, you can end up with answers that are incorrect. Inflection point is where the graph changes from concave up to concave down. Increase and decrease, we're dealing with the sign of the first derivative, and concave up and concave down, we're dealing with the sign. So if we're going back over to here, that's where these various ones came into place. Since these would both be the same, okay, we couldn't see them, we had to take it times a number. So we took the sign times 2 to get -2 and +2 so we could see where these graphs were. Here we have the information being shown on our calculator, and this is the same information shown over here. Notice the various warnings. So you're again going to have to deal with these warnings. Let's go over here and take a look at these warnings. So again, on your touchpad, when you work this stuff out, okay, if you just slightly go over it, then you can go over to here and click with your mouse, and it will tell you the domain of the result may be larger than the domain of the input. The same warning appears for all three. So again, this is what we have to watch out for, because remember when we were looking at the graph, the domain of these answers turned out to be such that they were between -1 and 1, but the original function was not true there. So therefore you could not take those answers. So again, you have to look at these warnings, understand them, and then apply them. Scrolling down some more on our screen, let's go to the next page. The next page shows this information. So if we go over to our calculator and scroll down, we see where we come up with this stuff. Now, when you start manipulating this stuff in calculus, you will have to use common denominator, okay, and factor to get answers to look like they are in your book. So again, you wouldn't necessarily know all this stuff when you first write it. We did, to make it look more efficient, put it down together in one line. But when you're working this in a calculus class, you're going to have to use the factor to change things into to times each other, the common denominator to take terms and change them into factor, and the factor to bring out common factors, okay, in there. So when you start working this stuff out, you get all kinds of information here again with all kinds of warnings. So again, let's go over here and take a look at these warnings. So we'll mouse over, and again, this is the domain one. Same thing about the domain one, and same thing about the domain one. So the domain one was true in all these different cases. Now, when we typed in 0, it said ±2. So this was telling us that we couldn't do the concave up and the concave down. be shown when we're taking a sign of it, because it gave us both of these answers. So again, there's some more hints and stuff with how these answers turn out. But even though this looks like it's really complex, these functions will turn out to be helpful to you when you're working in a calculus class and you're graphing all kinds of complex functions. One problem in a calculus class can end up taking a whole page of paper and can end up taking you a half an hour to work it out. So tools like this that can make you more efficient will allow you to work more problems, which will give you a better understanding of what's going on. Let's turn to page. Another thing that we can do is we can bring up our table and we can plug in the function, we can plug in the increase and decrease, the concave up and concave down, and put points in. Normally what we're going to do is have two separate tables. Again, for this class, since we're not actually doing all this material out, for this class we just put them together so you can see what's going on. Again, you will want to take a look at more of these. You want to go out here and study this in more detail to see what's happening. In this class, basically we're only going to have to do with the manipulation part, not the calculus part. But you can see that everything that you don't know in this class will hurt you when you're taking a calculus class. So try to get as much down as you can. Then use your calculator to help plug in the holes until you get all the information down. Our last problem we're going to work has to do with an apartment unit, where we have an 80-unit apartment complex that charges $500 rent. And we've noticed that for each $10 increase, okay, one person leaves. So if we had $510 rent times 79, we would take in $40,290. If we had 5 vacant, we would 75 times 550, we take in this. So we'd like to know how many units vacant and what the maximum revenue we could be, and that kind of information. So there's several ways we can work this problem. We could actually just work it out by arithmetic, listing them all out, and find the highest point. The easiest way to work this problem is to try to come up with a formula. So 80 minus x times 500 plus 10x. If we took a look at several of these listed, then we could see how this could lead up to this problem. Then once we have this problem, if we were doing it in our future volumes, when we're dealing with quadratics, we could complete the square, and we could end up, okay, with the maximum revenue being $42,215 with 15 vacancies in the problem. Or what we can do is we can work this problem by calculus. So when we're working this problem by calculus, this is what happens, and this is what happens with the maximums and minimums. And then we can go to our graph, and we can do our increase and decrease to show, like the first derivative test is when it goes from, okay, increasing to decreasing. At the highest point is where the maximum is. The first derivative test is something from calculus. And so we can see our scale 5, 10, 15, okay, in here. And if we put 15 and subtracted it from 80, that would give us, okay, 65 units. And then if we put in the 15 times 10, okay, that gives us 150 plus 500, rent of 650. And again, with our substituting both these in and multiplying out, that would give us 42,250. This concludes our Chapter 7 lesson. Thank you.